All right.
I don't.
Okay, so
Yeah, so I'm going to.
the one thing that, because this was my summary comment, if you ever have a vector that is given to you that is associated with an actual number of degrees in a problem, if you are comfortable enough with the idea that what I'm going to do is I'm going to rethink of this as two vectors that are perpendicular to each other, that is a good understanding knowledge, because we can't do our normal math of addition and subtraction when we have things at angles. We can do addition subtraction type stuff when we have things that lie in the same dimension. And if you think about the whole idea of 1 dimension, 2 dimension, 3 dimension, every additional dimension is added at a 90-degree angle from the prior two. And that's why this idea that when we say, well, 3 dimensions means you can go in any direction you want, in the big picture, yes. But if you want to do math in 3 dimensions, you have to take that, I'm just going in any angle I want, and break it into what are you doing, at least the way this connects with math, in the x, just in the x dimension, just in the y dimension, and just in the z dimension. And then once you break that vector into those pieces that are perpendicular to each other, you can isolate each dimension, and that's where you can do the addition and subtraction stuff. And then, unfortunately, if you're adding multiple stuff, you got to bring all those pieces back together to get what is the overall effect of the vector. So if you understand that as a concept, there's detailed math associated with it, but just that idea of realizing I really can't do math the way I normally do it when I'm given things with angles. And what I need to do is I need to rethink of those things at angles like this, then I can start to do math. Because really the only math we're going to do in each dimension is really addition, and that's it. Okay, so we need, when you think of 3 dimensions, if you get this 2-dimension stuff, the 3-dimension stuff, even though some people would say, damn, that must be like crazy, it's not really crazy. If you understand the 2-dimensional addition stuff, the 3-dimensional stuff isn't really all that much crazier. You just have to know what's the equation I need to isolate that z dimension. And it's not some really crazy looking math. Okay, now we need to revisit this step. Anybody remember what goes over what? Well, from yesterday, when we did this step, this was to figure out what was the angle of our answer. What went over what?
Ry over Rx.
Ry over Rx. It is always the vertical, at least in terms of xy dimension, it is always the vertical thing over the horizontal thing. Now we talked about a problem with this. And in order to explain how this is a problem, oh, I wonder if they're all picking this up. It's like, yes, they're playing something next door. I'm gonna try and illustrate the problem that we have with this, not by doing the inverse tangent, but by saying, what's the tangent of certain angles? And we'll just start with the easiest one, which is what? What's the easiest tangent?
45.
45. So if I have a 45-degree angle, and usually in math, they won't do this in terms of vectors, they'll just do it in terms of triangles. What is the value of that? 1. Oh, and, you know what we can do? Just because I love it. Unit circle. God, thing is. This thing is awesome.
That was a good circle. That was a good circle.
Was that all right?
Yeah.
Okay. It's left over from my high school days when I took a architectural drawing class. Only once. I'm going off on a tangent for those in video land, but whatever. This is normal experience for you guys. When you look back at some classes that you've taken, there are certain ones where you're like, damn, I am so glad I took that. But it's really not like this hardcore academic class. Architectural drawing was one. It was only a semester, but it taught, one, it's about making things very precise, which I liked. Plus, your workspace. Anybody ever seen like an architect's desk? Mm-hmm. It's cool. It's got the slight little angle to it, you know, and you think you're like, I'm going to make a building and all, you know, you were never getting anything that complicated. But it made you feel like it. You got this big workspace. It's perfectly smooth. You have all these toys that you got to play with to make things at just the right angle, at just the right length. I ate it up. It was awesome. But one of the things that they also teach you about is if you don't have the toys to make things perfect, how can you freehand things to try and make them look more accurate? And one of the things that I learned from that to this day, if you want to draw a shape, the last thing you want to do is follow the writing instrument as you're doing it. And what you need to do is you need to like step back and look at it from the big picture. So for example, if you wanted to go from here to here, you don't sit here and follow your writing instrument as you're trying to draw that straight line. You keep watching that dot, and it's like magic. It's like, that's not perfect, but if you forget about where you're going, you start to go, and then you're like, oops, oh, that's crap, I got to go back here. You always got to focus on where you're going. So in doing the circle thing, you can't like watch this. You have to like keep the big picture going so that in your brain, it's amazing what it's able to do. The other class that I took, that if I didn't take that, I wonder if I'd be a pecker on the keyboard. I took typing, and this was before word processing. We had to learn, you got to hit the key strong enough so that it'll actually leave ink on the paper. But I learned where all the keys are, so I'm a decent enough typer now simply because I took that class. I think they did have like keyboarding classes, which is, very practical for people to take. I think anybody actually had an official typing or keyboarding class? Or do you guys just freaking learn it because you're on it all the time?
I feel like we did like something with it in middle school.
Not your type.
Okay.
Yeah.
Not your type.
Okay, so back to this. Unit circle. What is the value of our tangent of 45 degrees? It's 1, because it is the length of this side over the length of this side. Anybody remember the exact value?
Root 2 over 2.
Very good. If we were on the unit circle, this is 1, this is root 2 over 2, and so is this. Okay? So, here's where the problem comes in. Is there another place where we get this value? What angle is it at?
225.
225, and I'll do this in a different color. That is this. But, and I guess I'm going to do this here. And I'm going to be very explicit here. That's how we get that one. But if we were to do we would still get 1, but how is this 1 different from that 1?
Negative.
It is formed because this is negative root 2 over 2, and this is negative root 2 over 2. Now I'm being really explicit here. So when you go to a calculator and you say, hey, I need the arctangent of 1, it actually has 2 possible answers, at least within 1 complete time around the unit circle. So when the people who developed calculators addressed this or ran into this issue, they had to make a decision. Where are we going to give an answer? Because we can't give both of them. Our calculator is not that smart. It is an incredible calculating machine, but it can't think. And it cannot, and most people, when they say, I need the arctangent, they don't go, because this is what you'd have to do. I want the arctangent of positive root 2 over 2 divided by positive root 2 over 2 versus I want the arctangent of negative root 2 over 2 divided by negative root 2 over 2. If you could teach a calculator to require that as an input, then you might be able to distinguish between these 2 spots. But they didn't. So they had to make a decision. And their decision was, when we do, and for our purposes, we're just worried about arctangent, but they do have this same issue with sine and cosine, because you have repetitive values as you go around the unit circle. They said, we are only going to give arctangent angles in the first quadrant and the fourth quadrant. And when you go, well, what about these? You'll have to figure that out. So when you are actually in the second and third quadrant, your calculator will never give you those angles. And you have to realize as you do your arctangent step, where the hell is my answer pointing in the first place? Okay? So we are going to address that here because this equation for our arctangent step is a good one. But we have to add just a little extra information so that depending on where you are, you might be able to list the answer for your, or the angle for your answer exactly as the number that comes off your calculator. Or you might have to take the number that your calculator gives you and play with it just a little bit. But in order to play with it the right way, one of the things you have to understand is what quadrant are you in to begin with. Okay, so I'm just going to give you, we're going to create the rules over here in black. If you are in quadrant 1, easiest of all of them, your calculator will give you the exact angle you need. Okay? And that means once you do an arctangent, if you're in the first quadrant, you don't have to do anything to the angle that your calculator gives you back. That's your angle. If you're in quadrant 2, and I'm going to do this, what color am I haven't used lines yet. If you're in quadrant 2, and I'm just going to make up an answer here. Let's say you have that vector as your answer, and you want this angle. Your calculator will not give you that angle. What it will give you is this angle. And how will it present? Now, this is the part that's going to make it easy. how will it present that angle to you on your calculator? Since you are going down in this direction. Wow, you guys haven't done this?
Negative?
It will give you a negative number of degrees. So it will say negative, I hate using theta again, but I'm going to use it. It'll give you a negative theta. If you actually want this one up here in solid, what could you do with this negative number to give you that correct number of degrees?
Subtract 180 degrees.
No,
Oh.
you're close.
Add 180.
Add.
Why add?
Because we need the positive number.
It'll already be negative. So if you're thinking, oh, well, if I had this theta, I would need to subtract it from 180 to get this one, your calculator is going to give you a negative number to begin with. So again, you don't have to do that subtraction. You just have to add 180 to it. So that means if you are in the second quadrant, you add 180 degrees. Okay? Now I gotta get rid of this so we can do the other ones. Well, I can continue this one. All right, let's say you are, I'm just gonna write over this stuff here. Let's say that is your answer. That means your angle that you need is that right there. Your calculator will give you that angle. So what would you need to do with this version? Again, I hate using theta twice, but this is what your calculator will give you. What will you do with this to get this complete angle?
-360
You could do it, but there's an easier thing since it's already giving you this number.
Add 180.
Add 180. And we're going, wow, that's just what we did on the last quadrant. Awesome. It's like a duplicate. This one here is 180 degrees further around. So if you are in quadrant 3, you add 180 degrees. Okay? Last one. Then we've covered all the quadrants. We're in quadrant 4. Now I gotta erase this crap again. Say that's your answer. So what you want is this one here, but your calculator can't give that to you. What it will give you is that angle as a negative number of degrees. So if it's giving you this as a negative number of degrees and you want this as a positive number of degrees, what would you do with this number to get the positive number of degrees?
You could add the negative value of a degree to 360.
Okay, so you would basically take what your calculator gives you and then just do plus 360. Okay, now in some math classes, they may end up saying, oh, well, I'll just take if you're down here in the fourth quadrant, I'll take the negative number of degrees. I don't take that here. we are in 2 dimensions, that means our directions could cover 0 all the way to 360. And because that's one of the ways that direction is kind of laid out for you, when you give me an answer in this big 2-dimensional kind of scenario, I want the answer to be from 0 to 360, always as a positive number of degrees. At higher levels, if they say, I'll take the negative number of degrees, I'll leave that to them. I always want this theta in your answer to be a positive number of degrees. So this is the 4th step, but this is the extra information you need. So now, here's the question. How the hell are you going to know whether you're in the 1st quadrant, 2nd quadrant, or 3rd quadrant, or 4th quadrant? Based on steps that you would already have gone through.
Could you just use the signs of the, not the SINA, but the SIGHN, of the RX and RY to like plot the point?
Right. Remember the step prior to, well, actually 2 steps prior to this, you figured out the value of Rx and Ry. Rx tells you whether you go this way or this way. Ry tells you whether you go this way or this way. And it's almost like a Cartesian coordinate system. Now I'm going to do this in blue. If you're in the 1st quadrant, what sign would be on your Rx? Positive. What sign would be on your Ry? Positive. This is going to be really repetitive. What is the pattern going to be if you're in the 2nd quadrant?
Negative, positive.
Rx would be negative because you need to go to the left, and Ry? Positive because you need to go up. I'll make that. If you're down here, I love being able to just like write over this crap and go, you guys get what I'm talking about. What's the sign pattern here?
Negative and negative.
Negative, negative. And over here, what is it?
Positive, negative.
Positive, negative. So at the moment that you are done with step 2, which was add all of the x components and all the y components together, in a way, if you're already looking down the road, you already know what quadrant your answer is going to point in. And based on knowing that, then you know which of these little extra rules you're going to need to apply so that you can get your correct answer. Now, I will say that when you go to do vector addition, at least, you know, the real straight up vector addition, this is the one place where people can go, oh, you got so much correct, and then you messed up at the end. This is probably the most frequently messed up step, okay? And because this one, it's in your head, okay? You know, just remembering this is one thing, but then this is like the extra that you need to keep in mind. And if you forget this, unless you're in the 1st quadrant, if you just write down what your calculator gives you, it won't be the right value, okay? So there'll be some kind of a ding on that one. Okay, you guys get this? All right? I hope you guys can see. I love this vector crap because there is so much that connects over to math that you've already been exposed to. So when someone goes, when the hell do I ever need to use this? Here you go, okay? Most people will go most of their life, if not all of their life, and never ever have to do this. But one day when you are parents and your kid has a vector thing and you start doing this, damn, you're pretty smart. Be like, yes, I am. Okay. Now we're going to summarize everything we've learned about vectors now. We'll put the equations up here. But this would be like my manual for vector addition. What's step 1? If we had to summarize it in equations, what are they? I said hand motion. I'm like, anybody? What did we do in step 1?
Draw the vectors.
Yes, what did we do?
We found the angle and the length of the vector, and then
And what did we do with that?
we added them.
No. We're only doing the mathematical
Okay.
addition. So you had your list, and you've already done this. What was the first thing you had to do with your vectors mathematically? Actually, it's the only thing you've done with them so far. See, I see people like, oh, say it, say it, say it.
Sit, Nick.
Nick knows.
No.
Great job. Great.
Nice try. Close.
You're great.
That's your first step. Anybody know how you would verbalize this? How would you in words explain to somebody what this is doing for you?
You're finding the horizontal and vertical components.
Right. You're finding the components of the vectors. Fancy word, resolution. You can say, we need to resolve the vectors. But if someone doesn't understand that, then the more explicit way is, we need to find the horizontal and vertical components of the vectors. Okay? What was the second step? This you can check your notes, because this is where we're going to yesterday.
Adding up the x components and the y components.
Right. And when we added up all of the x components, what was it that gave us? Rx. And if someone asked, well, what does Rx represent?
The x component of the resultant.
Right. And the resultant is our answer. So it's like, this is the horizontal piece of the answer. What's the other thing we did?
The same thing but for y.
Correct. All right. What was the third step? Come on, Sarah was gone for over a week and she is carrying you people. The rest of you have been here. What was the next one?
You solve for the resultant.
Okay, and it was not with the arrow.
The arc.
It was just the length. And how did we do this?
Square root of rx squared plus ry squared.
I just refer to this as the Pythagorean step. Okay? And then what is step 4?
What we just did.
Which involves what function?
Arctan.
Arctangent. So it is, we need to get theta, and we do that by doing the arctangent, and it's always what over what?
Ry over rx.
Ry over Rx. And this is where we have to add a little extra. First quadrant, what do we do?
Add 0 to b.
Basically nothing. And this is where we can consolidate a little bit, because if you're in the second or the third, even though they point in different quadrants, you do the same thing, which is what? Add 180. And then if you're fourth quadrant, add 360. So if we are ever discussing this process, resolution or component step, summation step, Pythagorean step, arctangent step. So hopefully, you know, when you're asking me for some help, I may look at your work and say, oh, You've already done this. You gotten this far. What's the next step? Boop, this one. And then you go here. Are we good? Okay. So here is going to be your assignment. And I think we have a little bit of time in class, but again, I only want this worked on here in class. So I'll have to pass your papers back to you. We had these three. What was the first problem I had you do when we added vectors? Was it b plus I? Come on, come on, come on. Yes? Who wrote these down? It's going to make me get my paper out. Okay. That was the first one. 2 was this one. And 3 was okay? And you did these graphically. Now, and everybody when they're doing these, they're always like, how much wiggle room do we have? Did I do it right? I'm going to have you do these 3 again, but I'm going to have you do them mathematically now. So you're going to use all of these steps here. And the beauty is, what step have you already done for all of them? You've already done this. You already have all of your pieces. You've calculated them. So what you need to do is now do these. Okay? Now, I did have one restriction, and this is the beauty of mathematical vectors, where I can say, if I give you an instruction, based on this instruction, when we get to the end, you and I should have exactly the same number. Whenever you do a calculation, what decimal place are you rounding to? The nearest hundredth. So these are already at the nearest hundredth. So when you add them together, these two pieces should still be nearest hundredth because they're not going to add any decimal places. Here, you're going to have to round to the nearest hundredth. And then here, when you do this step, you will have to round. But remember, these two values are already to the nearest hundredth here when you do the calculation. Yes?
So should we not round at the very end? We should.
Well, at the very end, when you get the number here, do the appropriate thing here, then do your round.
Okay, so.
Okay? So you're still rounding on the angle thing, but round after you've done this little adjustment.
But don't round for like step 3. Just do exact answers until the end.
Oh, here?
Yeah.
If you're the kind of person who says, look, I'm going to take a number to the hundredths here and square it, and then I'm going to round that to the nearest hundredth, don't do that.
Yeah.
Do this to the nearest hundredth, this to, and I'm looking at this like you're just going to set the whole thing up as one calculation. That you're not going to square this and then write a number down, and then square this, write a number down, and then re-enter them. You should be able to enter that on your calculator as it's written. Now, one thing I do want to point out, for my, computer programming people, you can program this into a calculator so that some of you, depending on what calculator you have, actually have vector capability on your calculator. But I'm not going to tell you how to access it. Now, one of the coolest things that I ever learned about, and I will tell you this, if you go into your mode, there is polar coordinate mode and rectangular coordinate mode. And if you set your calculator for rectangular coordinate mode and you enter a vector as a vector and hit enter, it will automatically spit out for you these two pieces, because in rectangular coordinate mode, it does not process vectors as magnitude, angle, it actually takes you through these two things and you see an ordered pair, X and Y. Totally kicks ass. But again, I'm not going to tell you how to access any of that. I'm going to leave that up to you. And some of you may have calculators where you can't do that. I'm some of the graphing calculators, I was almost disappointed when I'm like, damn, you shelled out $110 for this thing, and it won't do vectors. It won't do that for you. And there are some calculators that are actually cheaper than that will. There's one new one that will actually draw a picture of your vector addition too. It's like disgusting. Okay? It's like totally out of bounds. Some of your calculators, I want to say, you guys need to like be restricted from all those calculators till you get to a higher level. But that, what is it, that the cat's out of the bag on that one? I can't, or what is it? You can't put the genie back in the bottle. So you guys have so much more calculating power than you realize in your stuff. It's disgusting. And I will give one last plug. Spreadsheet. You could write a spreadsheet program for this, where you can just enter stuff and bam, just like all appear in other squares. Like here are the X values, here's the sum of these things, here's this. The one where you would have a little difficulty is this, because you'd have to figure out a way to tell the spreadsheet, okay, when you're in this quadrant, take the answer from this and adjust it by adding. So you might have to do that on your own. But you could put a spreadsheet together that would do this like pretty easily if you had to do it, a lot. Okay. I designed talking a little bit more so I could say, we can start this tomorrow, right? Because 10 minutes is too short to have you get started. Okay, so tomorrow I'm going to give you your mathematical resolution papers, and depending on how much free space you have on that paper, you may have to start with a second page. And what you're going to do is you're going to do these 3 problems, but you're going to do them mathematically now. All right, and we're going to see what you come out with. And I'm not a huge collaboration fan, but the idea is, in my head, the perfect way of doing this is for each of you to do, you've already done this step. I'm assuming that you have already checked with other people to make sure that you've gotten the same answers. So the next thing you're going to do is this step, and after you do this, you can check with your people to go, did we all get the same thing here? Then you can come do this one and double check and say, did we all get exactly the same thing? And then you can do this one, okay? And I kind of think that you'd be able to finish all of this tomorrow in class, unless I talk too much at the beginning of class, which is always a possibility. So somebody's got to keep me focused and tell me to be quiet. All right? All right, so that's it.